Hello everyone. This part of the course is about building a simple, fully connected neural network, also called a deep feed-forward network, and using it to classify handwritten digits from the MNIST dataset. Now, MNIST is kind of a go-to dataset in machine learning. It contains thousands of 28 by 28 grayscale images of handwritten digits 0 through 9. And our job is to train a neural network that can recognize and correctly classify them. So in this lesson, we will first load the data, then we will do a bit of pre-processing to make it ready for the model. After that, we will actually build the model itself layer by layer. And the idea here is to keep things clean and simple. We are not using convolutions or anything fancy yet. We just want a good baseline fully connected network to get started with. And let's look at the code and talk through each step. Okay, let me scroll. So here we are defining a function called load and preprocess MNIST. This is going to take care of two things for us: loading the MNIST dataset and making sure it is in the right shape and format before we feed into in a network. And okay, we start off by calling keras dataset MNIST load data, and that gives us 4 arrays: 2 for training data and 2 for test data. The inputs are images and targets are digit labels. Then right below that we normalize the pixel values. Why do we that? Because the raw pixel values go from 0 to 255. We scale them down to the range between 0 and 1 by dividing everything by 255. And this usually helps the network train faster and more stably. That's okay. And next we reshape the image. Here you can see, and originally each image is 28 by 28 pixels, so it's a 2-dimension array, but a fully connected layer expects a 1-dimension input, I mean just a flat vector. So we use dot reshape to turn each image from 28 by 28 into a single vector of length 784. That's okay, I hope. And after that we one-hot encode the labels. This just means instead of having a single number like 3 or 7 to represent a class, we create a vector of length 10, one element for each class, where only the correct index is set to 1 and the reset are zeros. It is a format expected by the loss function we will be using. And finally, we return all of our arrays, training inputs and labels, test inputs and labels. This function keeps our code clean and reusable. Now let's build the model. This function is called create deep feedforward network, and it takes 3 things as input: the shape of the input data, the number of neurons in each hidden layer, and the number of output classes. The model is built using keras sequential API, which basically means we are stacking layers one after another. And we start by adding an input layer. This is not a layer that learns anything, it's just telling the model what shape of the data to expect. In our case, the input shape will be 784 since we flattened the 28 by 28 images earlier. Okay. And then we go into the hidden layers here, and this part is a loop, as you can see. For each number in the hidden layers list, we add a dense layer with that many units. The activation function is value. It is the standard choice for hidden layers in most cases. Right after each dense layer, we add 2 more things: batch normalization and dropout. Batch normalization helps stabilize training by keeping activations in a healthy range. Dropout, on the other hand, randomly turns off a percentage of neurons during training. This helps reduce overfitting. That's okay. And here we are using a dropout rate of 0.3. That means during each training step, 30% of neurons in that layer will be randomly ignored. That's okay. And after we add all the hidden layers, we finish the model with an output layer. This one has as many units as we have classes, 10 for the digits 0 to 9. The activation is softmax, which turns the output into probabilities across the 10 classes. Finally, we compile the model. We are using the Adam optimizer with a learning rate of 0.001. That's a pretty standard starting point for most classification problems. And the loss function is here categorical cross entropy, which works well with one hot encoded labels. And for metrics, we are just tracking accuracy for now. The model is now ready to be trained. It has all the layers, it's compiled, and it knows how to update itself during training. Okay. So, now that we have our model ready, the next step is to train it. This function here is called train and evaluate, and it handles both training and testing in one place. We begin by setting aside a small portion of the training data used for validation. In this case, we are taking 10%. So if you have 60,000 training samples, about 6,000 will be used just for validation during training. And this helps us see how well the model is doing on unseen data while it is still learning. We split the arrays manually. We are not using any library function here, just slicing the NumPy arrays. And the first part goes to the validation. The rest stays in the training set. Next up, we create two callbacks. These are kind of like observers that monitor training while it is happening and step in when needed. The first one is early stopping. What it does is pretty simple. If the model's validation loss doesn't improve for 5 rounds in a row, it stops training early. And we have set it to bring back the best weights it saw along the way, which avoids overfitting toward the end. And the second one is reduce LR on plateau. If the validation loss stops improving for 3 rounds, it cuts the learning rate in half. The idea here is that sometimes the model gets stuck and a smaller learning rate might help it keep moving. And with that setup done, we start actual training. We use model fit pass in our slice training data, batch size, number of epochs, validation data, and the callbacks we defined. And once training finishes, we evaluate the model on the test sets. This gives us test loss and accuracy, and what really tells us how well the model generalizes. At the end, we return both training history and final accuracy. And plotting part is here. Okay, it is a good idea to visualize how it performs over time for training. And this helps us see whether the model is overfitting, underfitting, or training in a stable way. So this function, plot training history, does exactly that. It takes the history object returned by Keras. This object keeps track of metrics during training. We start by creating a white figure just to make space for two subplots side by side. On the left, we plot accuracy, both training and validation, and this shows us how the model improves its predictions over each epoch. Okay, and on the right, we plot the loss values, again, both training and validation. And watching both of these plots together can help us decide whether to add more epochs, increase regularization, or maybe adjust the architecture. And predictions here. So now we want to actually look at some of the predictions the model is making, just to get a sense of where it's getting things right or wrong. And this function is called visualize predictions, and we can use it to display a few test images along with their predicted and actual labels. And we start by making predictions using model predict, but we only do this for the first few samples. Default is 10. Then we convert those prediction vectors into class labels using np marks, both for predicted values and the true labels. Then we create a figure and go through each image one by one using a loop. Each image is reshaped back into 28 by 28, so we can display it using a imShow. Okay, and we turn off the axis ticks just to make things cleaner visually. For each image, we set the title as pred and true. If the prediction is correct, we color it green, otherwise it shows up in red. So this is a quick way to spot check if the model is working, and more importantly, to see what kind of mistakes it's making. And final part, let me scroll. Here's how everything comes together when we run the script, and this part at the bottom is entry point. So we run this point, run this Python file directly. This is what gets executed. We start by fixing the random seed, and this is done to make results reproducible. So if we run the code again, we will get the same model weights and outputs. Then we print a message and call our pre-processing function to load and prepare data. After that, we log the shape of the training and test data just as a sanity check. Then we define our model architecture. The input shape is 784. That's because each image is flattened into a one-dimensional array of 28 times 28. For the hidden layers, we have chosen 3 layers with 512, 256 and 128 neurons respectively. Output layers has 10 units, 1 for each digit class. And next we create the model using our earlier function and print a summary. This helps us double check the number of layers and parameters. Then we kick off training using the train and evaluate function we wrote before. We pass in everything it needs: training data, test data, number of epochs, and so on. And once training is done, we call plot training history to visualize how the model performed during training. And finally, we display a few test images with predicted and true labels using visualize predictions. Okay, and at the very end, we print the final test accuracy. That's the number that tells us how well the model did overall. Okay, code is done, and let's look at our outputs. So here is a full summary of our model after we have built it. This is a helpful overview showing what each layer is doing, how the output shapes are changing, and how many parameters we are working with. The first layer is dense layer with 512 neurons. Since our input is 784 values per image, that gives us just our 400,000 parameters, most of which are weights connecting inputs to neurons. Then we got batch normalization, which doesn't add parameters, just a few for scaling and shifting. After that, dropout has 0 parameters. It just randomly turns off some neurons during training. And we stack 2 more dense layers, one with 256 neurons and another with 128. Each one is followed by batch normalization and dropout again, so we are building up a solid multi-layer architecture with regularization built in. And the last layer has 10 neurons, one for each digit, and a softmax activation to produce class probabilities. And you can see the total number of parameters. What is that? 571,000 in total, and out of these around here are trainable, and that's what optimizer will be updating during training. And okay, let's look at how training progressed across the 15 epochs. In the first epoch, the accuracy is low. That's expected. It starts around 82%. But by the second epoch, we have already up to 94%. So the model is learning fast. And you will notice that both training and validation accuracy keep improving steadily. Loss also keeps going down, and that's a good sign. It means the model is not just memorizing the data, and it is actually generalizing well. We also keep an eye on learning rate, and here it stays at 0.001 for most of the time. But near the very end, starting from epoch 13, you will see that the learning rate is cut in half. That's because of the reduced LR on plateau callback we added earlier. Remember, it noticed that the model wasn't improving much and decided to slow down learning. And by the last epoch, we hit a training accuracy of about 99.2% and validation accuracy around 98.2%. That's pretty solid performance for a simple, fully connected network. And okay, let's take a look at the training curves. On the left, here we have accuracy. The blue line is training accuracy and the orange line is validation accuracy. You will notice they follow each other closely, which is good. If they were far apart, it would mean we are outfitting, but here they both go up and stay near each other, so the model seems to be learning in a balanced way. On the right, we see the loss curves, same color coding here. Training loss keeps dropping smoothly, validation loss also drops at first, then sort of levels off with some fluctuations, nothing unusual. Overall, this is what we want to see. The model improves consistently, there is no major divergence between training and validation, and the loss goes down without spikes. And okay, here we are visualizing some of actual predictions. Everything is clear, I hope. Each of these an image from the test sets. On top of every image, we are showing the predicted label and the true label. If the model got it right, the text is green. If it got it wrong, it would be red, but in this case all of them are green, which means it nailed every prediction in this batch. And you can see we have got a variety. There is a 7, a 2, a 1, a 0, and so on, and the model seems to have no trouble identifying them. So this kind of visual confirmation is helpful. It reassures us that the model is not just performing well in terms of numbers. It is actually making accurate predictions that make sense visually. And when you look at the final test accuracy, here our value 0.98, and it is a really good performance. And okay, that's all for this lesson, and thank you for listening. See you in the next class.